Hello, this is Quincy and this is Physics 1 Lab 3, Black Holes and Orbits. The goal of this lab is to find the mass of a black hole using a computational model that shows the gravitational interaction between a star of known mass and the black hole. Then we want to use this mass to find the initial velocity for the spaceship to fly close to the black hole but not enter or hit the planet. We found the mass of the black hole to be 2.44 times 10 to the 34th kilograms and the initial velocity of the spaceship to be negative 4.8 times 10 to the 7th, 2.5 times 10 to the 6th, 0 meters per second. Key physics concepts are Newton's second law, which gives us the velocity update and position update formulas. Force equals mass times acceleration can be edited to be force equals change in momentum over change in time. And then we have the velocity update formula, which is Vf equals Vi plus F net over m times delta t. And then the position update formula, which is Rf equals Ri plus V average times delta t. And these help us update the position and velocity at each iteration. Another important thing to note is that the net force has a parallel and perpendicular component since we are talking about orbitals, which are a type of curving motion. Parallel components are tangent to the trajectory and they're related to the change in momentum. Perpendicular components are towards the center of the orbit and are related to the change in the direction of the momentum. So one is the change in speed and one is the change in direction. And then the last concept is universal gravitation. Because we are in space, there's a gravitational attraction between objects, and in this case that's the planets and the black hole in the spaceship. These are the two free body diagrams that we need for this lab. In the first diagram, you can see that there's only gravitational attraction between the star and the black hole, represented by the arrows directed towards each other. These are equal and opposite because neither is moving in this scenario. The star is far enough away that it is not getting pulled into the black hole. In part 2, there is a spaceship which experiences gravitational forces from both the black hole and the planet, and this is represented by the extra arrows on this graph. These are the two forces that we are trying to balance so that the spaceship can safely travel close to the black hole without getting sucked into its orbit or crashing into the planet's orbit. In the first graph, the system is the star and the surroundings are the black hole, and in part 2, the system is the star and the planet and the surroundings is the black hole in space. This was my code to initialize the gravitational constant, the mass of the star, and the delta t, specifically in lines 123 and 126. This was my code to update the initial and final momentum, change in velocity, change in momentum, and calculate the parallel and perpendicular components of Fnet. The first image shows the updating of equations, and the second slide shows the code to find the mass of the black hole using iterations and the update formula from the first slide. I got a net force magnitude of 1.07 times 10 to the 29th newtons, a parallel component of 4.63 times 10 to the 27th newtons, and a perpendicular component of 1.07 times 10 to the 29th newtons. And then I used that to calculate the mass of the black hole to be 2.44 times 10 to the 34th kilograms. Rounding values during each iteration and rounding for the gravitational constant g would yield slight differences in the mass of the black hole at each iteration, which could add up especially with a large delta t where there are multiple iterations. For part 2, we used the mass of the asteroid from part 1 to update the position and velocity for the planet and the ship velocity. This allowed us to calculate the velocity the ship could move at without being pulled into the black hole or the planet by their gravitational forces. The spaceship speeds up as it gets closer to the black hole because of the increasing attractive gravitational force due to decreasing distance. However, we want to calculate the right initial speed for it to reach a speed that is greater than the escape speed so that it could fly close to the black hole, but reach that escape speed and be able to escape the gravitational pull before it gets too close and gets sucked into the gravitational pull. Possible sources of error include the rounded values for the gravitational constant g and the mass we calculated in part 1, which would lead to rounding errors. This slight miscalculation could change the outcome of the spaceship's velocity because there are a lot of factors, so one small difference in a number could turn out to really affect the final calculation, especially if it is used a lot in the updating. What does it mean that the parallel and perpendicular components of net force are different from the rate of change of momentum in its parallel and perpendicular components? This is because Fnet requires knowing the black hole's mass, whereas the rate of change of momentum allows us to solve for that mass using the position and velocity. We don't need mass to calculate the momentum, which allows us to do this problem. What if this imaginary system has a black hole, a star, a planet, and a moon? So if we wanted to predict the motion of the entire system, we would need to include the masses and velocities of the four bodies in our computational model. This would include the moon, as we already have calculated for the black hole, the star, and the planet. We could have a smaller velocity of the spaceship because the added mass in the system would add a gravitational pull in different directions that aren't into the black hole's gravitational pull. So this would further prevent the spaceship from falling into the black hole. Thank you.